Chapter 12, Smoke Control and Management Systems. Our objectives: define the terms smoke control and smoke management. State the design goals for smoke control and smoke management systems. Name the 3 general methods used to control smoke movement. Describe the 4 pressure differential methods used to control smoke. And describe 5 design requirements of operational characteristics of smoke control systems. List the different life safety and fire protection systems that interact with smoke control systems and describe how they interact. Discuss the importance of the acceptance testing and annual testing of smoke control and management systems. During a fire, smoke and toxic gases can migrate outside the fire area and throughout a structure. Exposed areas include stairways, corridors, elevators, ductwork, air shaft, utility shaft, atriums and openings or breaches in walls or ceilings. Smoke and toxic gases can cause as much damage and injury and death as burns can. Statistically, more fire deaths and injuries result from smoke and toxic gas inhalation than burns. Smoke control and management systems were added to the fire protection arsenal in the early 1970s, making them a relatively new development. Smoke control is a term that describes mechanical systems that pressurize areas of the building with fans to limit smoke movement from a fire. Smoke management is a term that describes passive and active systems used alone or together to alter the smoke's movement. The life safety objective of smoke control management system is to provide a tenable environment in the areas next to the fire area for building occupants and firefighters, and also to confine the smoke to the area of origin. This allows occupants to evacuate safely. This also allows firefighter relocation within a structure or management of the smoke intensity to facilitate the fire department operations. There are 2 general design approaches for these systems. A passive design approach utilizes walls, bulkheads, doors, partitions, draft, curtains, high ceilings, and sealed floor openings to create a barrier. This approach incorporates fire-retardant constructions to contain and minimize smoke leakage. Smoke and heat vents direct smoke and hot gases up and out of the building. The draft curtains sectionalize a building to contain the smoke and speed up vent activation. Active design approach utilizes mechanical systems to exhaust pressure and in some situations oppose smoke with forced air. Most mechanical systems operate when they receive a signal from a fire protection system initiating device that has detected or reacted to a fire condition in the protected structure. The choice of system, whether it be passive, active, or combination, depends on a variety of factors. Those factors include the particular structure or occupancy design intent, the appropriateness for the condition, an evaluation of smoke movement influenced by physical design, and architectural features of the building. The physical design and architectural features facilitate smoke movement throughout a building in obvious and non-obvious ways. The obvious path includes stairways, elevators, air shafts, and ductworks. Not so obvious pathways include unsealed construction openings at the interfaces of floors and perimeter walls, unsealed annular spaces around pipes, ducts and conduits through the floor shaft, incomplete shaft wall seals and smoke barrier walls at the junction of overhead floor structures. The smoke spread is influenced by other factors as well, such as buoyancy forces, stack effect, exterior wind and resulting forces, climate, function and control of heating, ventilation and HVA systems, expansion forces as air is heated, and fuel load. Code mandated installation of smoke control management systems is limited to certain categories of structures and occupancy classifications. The design of many buildings facilitate quick evacuation, inhibit smoke movement, and include fire protection systems, and does not present a moderate life safety or fire risk. Installation of smoke control and management systems thus is not particularly or cost-effective in all situations. Smoke control, removal, and management requirements exist in model code for your high-rise buildings, atriums, covered malls, underground buildings, stages, platforms, technical production areas, detention and correctional facilities, and assembly, health, and ambulatory care facilities. These structures have evacuation challenges and require increased life safety and fire protection features. The basic goal of smoke control and management is to maintain tenability throughout a building by mitigating smoke spread beyond the area or volume of fire origin or containing it completely within that space. Smoke control techniques can be standalone or integrated into building-wide smoke management systems. All systems discussed here use 100% outdoor air for positive pressure and smoke relief systems, with 100% exhaust to the outdoors to contain and relieve smoke. The three general methods are contained, removal, and opposed airflow. Contaminated by pressure differentials. Creating an adequate pressure differential between affected and surrounding unaffected areas, in particular egress paths, help with effective smoke control. Often, relative low pressure differentials can reduce the spread of or even contain the smoke. Pressure is one of the most commonly used methods of smoke control. Design requirements for low pressure differential systems are outlined in model building code standards and publications, such as NFPA 92, 92A, 92B. Publications from the American Society of Heating, Refrigeration, and Air Conditioning Engineers Incorporated also have additional information. Stairway pressurization systems prevent or substantially reduce smoke intrusion into egress stairways so occupants can use them to exit and firefighters can stage in a relatively smoke-free environment. Mechanical fans pump 100% outdoor air into the stairway, creating a pressurized barrier to prevent the smoke from migrating in. These systems perform best when they are combined with smoke removal, relief, or affected fire floors. There are several design considerations that can affect performance, such as the type of construction material used, the construction gap leak, multiple doors opening simultaneously or being propped open, the number of stair levels, and the pressure difference should not make it so hard to open the doors. Requirements for stairway pressurizations are included in the model building code and are common in high-rises. Floating zone floor-by-floor pressurization, also known as the sandwich effect or containment method, use the basic components of an HVA system to create negative pressure on the fire floors while applying a positive pressure above and below. These systems may be used in high-rises in addition to stairway pressurization. In addition to removing smoke-laden air, Outside air flows to all other floors. Outside air also moves from the pressurized floor to exhausted floors through gaps and cracks. Because air moves from high pressure to low pressure areas throughout the path of least resistance, some of these systems provide pressurization in stairways and elevators. Elevator hoistway pressurization systems operate similarly to stairway pressurization in that mechanical fans pump outdoor air into the hoseway and create pressure barriers to prevent or substantially reduce the smoke intrusion. Some design professionals think it is better to operate these systems as part of a complete smoke management system that includes zones or floor-by-floor systems, because standalone pressurization may not be adequate. Other design professionals believe hoseway pressurization is unnecessary and are concerned about the requirements for elevator doors to remain open when recalled to their designated floor level. If doors stay open, a major opening in the pressured hoseway occurs. The concern can be addressed by having doors open and shut at intervals. Firefighters can also use elevator keys to take control of the elevator cabs. Refuge area pressurization prevents or reduces the smoke intrusion into those refuge areas. Refuge areas are typically located on each floor of a high-rise within or adjacent to a stairwell or within elevator lobbies. Refuge areas are constructed with fire-rated materials and self-closing fire-rated doors. Refuge areas are holding areas for people who are unable to exit a building unassisted in an emergency. They maintain a tenable environment until rescue personnel can evacuate them. Typically, refuge area pressurization is combined with elevator hoistway pressurization or stairway pressurization as part of a comprehensive strategy. Smoke removal. This strategy is best suited for large volume spaces, such as atriums, airport terminals, and indoor malls. Sometimes smoke removal systems can help create a tenable environment in egress corridors, associated elevator lobbies, and refuge areas. These provide vertical cross-flow ventilation from floor to roof or horizontal cross-flow ventilation from non-fire to fire areas. Large volume areas have no physical barriers to restrict smoke movement. Smoke and toxic gases can rise and spread through open surfaces. The lack of restriction causes other problems in addition to large amounts of smoke and gas. Delay activation of automatic sprinklers and fire detectors. Damaged building components and equipment. To overcome these problems, unpolluted air from a lower level is fed up at a slower rate than the exhaust system rate. This enables one or more mechanical fans near the upper level to exhaust the smoke. Containment by airflow direction. When the pressure differential strategy is not practical, airflow velocity can control smoke across openings. A large volume of air flowing in a particular direction prevents smoke and gas from moving into the area of buildings. Manipulating airflow is common for managing fires in railway, subway, or vehicle tunnels. It is the least common containment strategy because the complex control and large air volumes needed to make it work. There are also concerns that air could feed the fire's growth by providing more oxygen. The design of smoke control management systems is challenging because each situation and installation is unique. It is important to be familiar with all requirements of the adopted model code and standard. There are some differences between the codes. Operational requirements in the model code include immediate and automatic operations upon activation of water flow devices, smoke detectors, manual operation and override, primary backup power source, minimum operating time, and the ability to maintain smoke levels at 6 feet above the highest level of seating or walking surfaces in the means of egress. Without automatic or manual detection and suppression, even the best passive and mechanical smoke control system may be overwhelmed by the fire. Proper operation, fire detection systems, and automatic sprinkler systems, coupled with rapid firefighter response, is the best way to control smoke and toxic gases. Interface with fire protection systems and other life-saving systems. Smoke control and management systems interact with your fire protection systems. HVAC systems, elevator systems, and backup power systems to initiate the appropriate control sequence and response when a fire emergency arises. During the design phase, smoke control zones, fire sprinkler zones, and fire alarm and detection zones are coordinated to establish the operational relationship between them. Dampers on air supply and relief systems will close. HVAC systems turn on or shut down. Elevators can locate at predetermined floor levels. And backup power systems are ready in case of loss of power to the smoke control system. Usual activation of automatic initiating devices start the operation of the smoke control system. In some cases, any water flow or detection device will start the system. In other cases, the initiation device must be near or within the protected smoke control zone to initiate the smoke control. Manual activation is also required. Any HVAC system failing to shut down can be the strongest contributor to smoke movement. Most HVAC systems interface with other systems and detectors and shut down, close, or open and turn to control smoke movement. If the HVAC system and its components respond correctly, the only path left for the smoke is the stairways or elevator hoistways, which are often pressurized to prevent penetration by smoke. Smoke detectors in elevator lobbies interface with elevator control systems to establish recall priorities during an emergency. In some jurisdictions, all smoke detectors and possibility all initiating devices interface with the elevator control to perform a recall. The most common recall method is to recall the elevator to the primary or alternative exit floor and to park the cab with the doors open. However, this does not result in significant loss of pressurization performance. Some elevators' doors have been adjusted to close after certain time intervals. Cabs are checked for people first. Some codes allow motorized damper installations and the fixed ventilation openings at the top of the elevator hoistway. Smoke detectors mounted at the top of the hoistway can open the dampers. The dampers improve pressurization and mitigation of the winter stack effect. Smoke control systems require both normal and emergency power sources. If the primary power source is lost, they can continue to run. With emergency power is provided, all components of the system must be reliable and functioning. The functioning components of a smoke control system always require monitoring to indicate the status of all equipment. Operational controls are also required for each smoke zone. The smoke control panel must have status indication and control functions that include the location of each major system by floor, shaft, or equipment room location. All components must be clearly labeled. The control panel in the same room as the fire alarm system control panel are often life safety system monitoring and controlling equipment. Acceptance testing. The design professional developed a detailed testing plan that provides a description of the smoke control system, the design criteria, and how they will be demonstrated and proven, what will constitute a successful performance, and a step-by-step procedure, the test instrument and equipment to be used. The test usually occurs after all other life safety and fire protection systems have been tested and approved. The smoke management system depends on these other systems. Testing is similar to that of other fire protection systems. It begins with an operational test at the company level. At the component level. Next is the functional test of individual systems. Functional and integrated performance tests involves recording the following: system response time, air pressure differential across the smoke barrier, door opening forces in the direction of egress. If pressure differentials are inconclusive, it is possible to generate an artificial smoke fog or visual confirmation of performance. This is not widely accepted as an actual representation of smoke and gas conditions that would be present once smoke is cooled by a fire suppression system. It may be used to show the amount of time necessary to achieve the acceptable level of visibility through smoke removal in an effective zone. All final tests must be witnessed and documented by the testing agent, engineer of record, approved authority, and fire department personnel. The building owner, operational, and maintenance personnel should also be present for testing so they understand the system. Final reports are prepared and submitted to the approving authority. The final approved test report is kept in the building fire control room and the building management office. Annual testing. To ensure proper operation throughout the life of the building, smoke control systems should undergo annual functional and performance tests. This is required by many state and local jurisdictions, just like the protection system. The testing should address individual components as well as integrated performance. Procedures are similar to those established during the initial acceptance test. The owner's personnel can provide individual component testing, but the individual system and integrated performance testing should be conducted and documented by the same individual who did the initial acceptance test. Without annual testing, smoke control systems can rapidly fail into disrepair or fail performance. This is especially true for multi-tenant office buildings during the initial build-out or first-generation tenants. Problems may be a result of multiple factors: reprogramming of the fire alarm system, electrical disconnect systems due to nuisance operation, and dampering motors failing to operate, initial disconnect damper linkage, or fan motors tripped on thermal overload. Verification of these control sequences and responses occur during the final acceptance phase of construction, and then the owner is responsible for that annual testing throughout the life of the building. Smoke control and management systems can provide a tenable environment or contain smoke in the area of origin so occupants can exit a building and firefighters can move or stage during a fire incident. The three general methods of smoke control are contaminate, exhaust, or opposed airflow. The choice greatly depends on the physical design and architectural features of the building. Containment is the most common used method of smoke control and depends on establishing pressure differences between the protected area and the fire area. Typical pressure differential methods include stairway pressurization, floating zone, or floor-by-floor pressurization, elevator hoistway pressurization, and refuge area pressurization as well. Smoke removal is common for large volume spaces, but opposed airflow is another option to prevent smoke and gas from flowing through large unprotected openings. In order to ensure appropriate system-wide operation, it is extremely important that smoke control systems are interconnected with the fire protection systems, HVAC systems, elevator systems, and backup power systems. The design of smoke control and smoke management systems offer the design professional many challenges, but a well-designed, installed, and maintained system will provide building occupants and firefighters the tenable environment necessary to evacuate, relocate, or stage during a fire emergency. Acceptance testing and annual retesting verifies the system performance as designed and is based on a detailed test plan that provides the description of the smoke control system, the design criteria, how these criteria will be demonstrated and proven, and what will constitute successful performance, the step-by-step procedures, and the test instrumentation and equipment used. Okay, gang, so we covered a lot in this chapter. If you have any questions, you can call me in the office at 706-357-0162, or you can email me at aroberts@athenstech.edu. Until next time, be safe and have a wonderful day.